Good afternoon, everyone. I hope you enjoyed the morning sessions as we continue the afternoon and the evening sessions. We have a lot of surprises, and we'll continue with the Professor Mehdi Bennis talk. And it's a pleasure to have Professor Mehdi Bennis with us today, and a great pleasure to bring his expertise to our stage. So Professor Mehdi Bennis is a full professor at the Center of Wireless Communications at the University of Oulu in Finland, and the head of Intelligent Connectivity and Network Systems Group, ICON, specializing in radio resource management, game theory, distributed AI and 5G and 6G networks, among others. So Professor Bennis is also an IEEE fellow with remarkable record of over 300 research publications, and he has made substantial contributions to his field of expertise. With his exceptional work, he has been the recipient of numerous prestigious awards, including the Fred Ellersick Prize in 2015, IEEE Communication Society's Best Tutorial Prize in 2016, several Best Paper Awards at prestigious conferences such as the EURASIP 2017, All University of Oulu Awards for Research, and a recognition as 2020-22. Clarivate highly cited researchers. It's a great honor to have you here, Professor Mehdi Bennis. We'll be talking about wireless edge, intelligence, the present and the future. The floor is yours, Professor Bennis, and it's a great pleasure to have you.
Thank you very much. Let me just share my pointer. So thank you very much again for this invitation. It's my pleasure to be with you today and share with you some results related to this area of wireless edge AI, which is actually an interesting area which kind of connects communication theory, information theory, and machine learning. Let me just put this here. Oops. Okay. So the outline will be as follows. So first, I'll talk about some current work in this area. So a number of techniques, including federated learning, federated distillation, split learning, and how we did apply them in various applications. And then I'll move on to the more kind of exciting, maybe down the road vision. We call it VisionX, and it will be about mainly semantic communication, which is in fact the post-Shannon communication theory, which will certainly impact also machine learning. So it all goes down or back to centralized machine learning, right? Where you had your devices, which could be sensors, vehicles, smartphones, sharing data to the cloud, right? And cloud takes care of the training and inference. Back in those days, at least, privacy was not an issue. From a wireless perspective, this incurs very high bandwidth constraint, latency, and so on. Then surprisingly, or interestingly, I should say, in 2017, Google came up with this idea of, instead of communicating raw data, we communicate models, right, over the air towards the server, and then the server will just aggregate these models and then send them back to the device. So device here are resource constrained, could be a vehicle, a drone, smartwatch, anything that you want. So this is actually very interesting from a bandwidth efficient perspective, because you communicate not the raw data, which can be high dimensional, but kind of a compressed representation of it. It's also privacy preserving to some extent. We know that there's some data leakage still. And you use the server to do different function, to average, aggregate, or maybe some more computational functions, right? You can also try to get rid of Google, which is maybe hard, and then you can actually try to train a model in a fully distributed manner. This could be your robotic arms in a factory. This could be your drones, right? So this, of course, scales much more than just relying on a single point of failure, right? Now, just for some historical record here. So in fact, so Google invited a number of people from different areas. You can find me here back in 2019, and their strategic plan was essentially to kind of connect the different disciplines and try to push for their federated learning idea, which in fact, now looking back, is a fairly easy idea. But we are maybe 2023, there has been an exponential increase in publications in this area, okay? Now, what interests me in this talk, in fact, is really this marriage between, on one hand, machine learning and wireless communication. So we have a number of constraints, for example, in wireless, for those who know. So we have, channel dynamics. You may have a noise in your channel, you may have interference. Bandwidth is usually limited. And then you have spatiotemporal dynamics, right? So the number of users may change from one set to another. And then on the other hand, from a machine learning perspective here, we are no longer in the big data paradigm, but in the more small data paradigm where, we have a number of devices. Every device has limited number of samples. You have resource constraints, memory, compute, bandwidth, and typically data is non-IID, right? So this marriage between this wireless communication or networking and machine learning brings about very interesting problems. For example, how do you train a machine learning model in a distributed, communication efficient, low latency, reliable, and scalable manner? You can also look at it from an inference perspective here, or if you are maybe familiar with more control theory or even reinforcement learning, you can try to also look at it from this perspective, right? Now, for the sake of my talk, I'll focus on a number of techniques. So I call them a zoo of techniques because, in fact, there are so many, and the area is rapidly moving. But for me, I'll focus on three families. So the first family will be the federated learning family, right? You have this model parametric change between devices and the server and the helper. We also see that sometimes there's no need for a server, or maybe you have some cases when there is simply not a server around you, right? In the second family, I focus on model output exchange here. The idea is instead of sharing all your weights, which could be really billion weights, you can share something called logit, and I'll explain you what we have done there. We propose this idea of federated distillation, right? And then a third family, which is split learning or model partitioning, which is also quite interesting in the sense that it finds many applications in wireless, but of course other areas. Okay. So let's focus on the first family, right? So I guess many people in the audience know how federated learning works. It's a very easy idea. You have a number of distributed or dispersed nodes. Every node has a number of data samples. And then what you do, you run your stochastic gradient descent or other maybe second order methods. You share your models over the air to the helper. And the helper just basically averages these models and send them back to the device, and this continues until some sort of convergence. Mathematically, it's really high school algebra to some extent. What we do know now, since FL came, that of course the performance typically is sensitive. If you plot, let's say, the test accuracy for MNIST or CIFAR10 or others, you will know that with non-IID data, the performance drastically drop, right? We also know now the federated averaging or the vanilla FL typically has been kind of unfair because it's been kind of minimizing some loss over workers. So in other words, there's this issue of unfairness where some users, some workers have very low accuracy compared to the others. So of course, we want them to really push them all the way on the right or strike a trade-off between test accuracy and fairness. Now, in what was actually the first application of federated learning in the 5G era of 5G discipline, my area, is the following. So we have a number of vehicles, you can see them here, and we want these vehicles to communicate what we call traffic messages to their intended receiver. So one vehicle communicates with the other vehicle. And we want to ensure that there is a delay constraint here, which hopefully you can see with me here. This says that the probability of latency has to be upper bounded by some parameter Q threshold smaller than epsilon. Now, to solve this problem, the vehicle does not have access to this network-wide latency, and therefore it has to learn it from data. So you could do it in many ways. For us, what we did, we really used the notion of federated learning. In other words, the data, which are the delay packets of every vehicle, right? You will locally run your stochastic gradient descent or other algorithm, and then you would share these model parameters over the air to a server. Now, because we are concerned with the reliability of communication, if you see with me here, this is a distribution of my Q length or latency. We need to, in fact, to characterize this tail distribution here and go after this blue part, which is related to the extreme event, right? So here, I don't know, maybe some of you are familiar with this mathematical framework of extreme value theory. We really want to be not in the average sense. I don't care about the average latency, but the highest tiles, right? Or the tail distribution of this latency. And then, of course, what you could do, you can invoke, there are famous theorems for extreme value theory. There is this Balke-Madehan theorem, which allows us actually to characterize the conditional CDF of this excess value, right? Which is, you see here on the blue. You can actually mathematically write it. So in fact, what we do, we just now formulate a maximum likelihood problem where we learn the shape and scale parameters of this distribution. Now, what's maybe interesting for this talk is to show that, in fact, if you compare the centralized approach, which is here in circles, right? This is where the vehicles send all their data to the server, right? Versus the extreme value theory FL, which shares obviously just the models. So you can see, in fact, that we can reach the same reliability as a centralized approach, but in fact, we get a free meal in the sense that we communicate much less number of packets compared to the centralized approach, of course, perhaps expected. But this gap should be even larger when we consider, let's say, high definition maps for, let's say, your Tesla vehicle, since this gap is only in the case, for example, in this traffic safety, we're talking about 32-byte messages, okay? Now, of course, as I told you, there's no need to stick to the server, right? So we can also move on to the serverless case or the fully distributed setting, because sometimes you have sensors, devices, which are very far away from the server, meaning the base station or the gateway or the aggregator. So there's no point to ask the device to really shout and push his model all the way to the server. Maybe it would just run out of transmit power. Therefore, we just try to formulate a completely fully distributed setting, which is formulated here. We use this known technique of ADMM, right? So alternative direction of method of multiplier, where in fact now what we do, we don't have a server. We divide all our clients in terms of 2 clusters, 2 groups. Obviously, you can do more than that. And then now, as you can see here, there is no joint constraints between these workers or clients. And therefore, what they do is just update their primal variable, right? Share it with the 2 immediate neighbors. They update their model, and then you update your dual, of course, variable, and then you send this back to the head group. So as you can see here, we can really have a kind of mathematical formulation of a setting where we have 2 clusters, and maybe you can see here I have a kind of chained like topology. Okay. Now for the result, we compare this for kind of linear regression task. Very simple. This is your test accuracy, number of iterations, a number of baselines here, gradient descent. Some baselines back in 2019, NIRIPS, you had this lazily aggregated gradient descent, and our approach is somewhere here, right? So group ADMM for different values of rho, which is this consensus penalty that is factored in the constraint. So you can see here, in fact, that you have huge gains. I mean, expected gains perhaps when you go from a server to a fully distributed setting. Not only that, you can see, for example, also here, if you plot it with versus the communication cost. So this was the number of iterations, right? If you plot it with respect to the cumulative communication cost, you can see again you have a huge gain, right? You can also perhaps see that this impact of this consensus or disagreement penalty is also playing a role here, right? When you go from, let's say, rho equals 3 to 5 to 7, right? So this is a way somehow to indirectly capture this non-IIDness of the data distribution. This was in this static setting. You can also try to see what happens if you go to a dynamic case where we allow over different epochs or iterations that a worker here can change his neighbor. So there's no need to always communicate with the same neighbors. You can randomly choose your 2 immediate neighbors, and we can actually show that this still converges to the optimal solution. Okay, so a kind of fairly easy idea here. Of course, we have to prove the convergence of the algorithm as a key contribution. Now, as you also know, the normal track here is to ask the question, can I now see whether I can quantize my model from 32-bit to 1 or 2 bits and see what kind of hits I take in my accuracy? So that's exactly what we did, following the same ADMM framework. Now, when you quantize your model, as you know, you might run into issues. So if there's a quantization error which propagates in the network, well, the algorithm doesn't work, right? It doesn't converge. So here what we did, we designed this algorithm where you need to essentially to find the right quantization range, quantization resolution, and make sure that asymptotically these errors, in fact, vanish asymptotically, okay? Now, if you apply this to the previous example, you can see here, if I plot the test accuracy or loss versus number of communication round, there is a huge gain here when I go, let's say, from, this is a 32-bit, right? This is a 2 bits. So we can see that here there is 0 loss in accuracy. What's maybe better, I can actually look, this is the gain I get in terms of transmitted number of bits. I mean, 10x easily gain here. So of course, here there is a free meal, but obviously this will always depend on the scenario. What we do know is there is an accuracy accuracy kind of quantization trade-off to explore. Okay. We also try to relax, because you can see here, I told you I have a chain topology, but there is no need for that. We can actually now allow a worker to talk to k number of workers, right? And that's what you call the generic bipartite graph topology. You can also come up with another idea where now we're exploiting the spatial degree of freedom, but also most of the time the workers should not actually share their model, because there is no informative kind of update that's useful for the algorithm. And therefore, what we did, we kind of designed this censoring strategy, which tells us when the worker should communicate his model update to each neighbor. And you can see that, in fact, what it says is we're compounding the gains. You see, you can go here from the pink curve here, which is the first JDMF framework, down to the left, right? So huge gains once you combine, obviously, the time, spatial, and also when to communicate. All right. Now, maybe a more interesting questions now, which talk about the co-design of really wireless. So what kind of properties wireless channels gives us that, let's say, somebody working in pure AI does not care about, perhaps abstract wireless communication. Here I'll show you, in fact, what's happening when you do the co-design. So for that, allow me to essentially kind of taxonomize the literature. So from a wireless perspective, if you want to implement FL, there's a huge problem, because these devices will be in the 100,000 or million, let's say, and they need to find resources, wireless resources, to push their over-the-air update, right? So of course, to do it, you need to call wireless engineers, right? So you probably need to have a huge spectrum to do that, and that's not going to be scalable, right? Moreover, you need to avoid interference, because of course, if many devices communicate on the same channel, well, we know what happens in Wi-Fi, for example. Therefore, we came up with a completely different, we kind of flip this paradigm, where now, instead of avoiding interference, we will harness it. Why? It's because, in fact, leveraging the fundamentals of information theory in the uplink, which is called the medium access control or MAC channel, in fact, we need to make sure, if we can, obviously, that we can leverage the superposition of the wireless channel, the inherent nature of the wireless channel in the uplink, to average perhaps in one slot or maybe 2, 3, 4 slots. Not only that, in fact, we will, so in machine learning, typically to hide your models, you add some noise, Laplacian noise, Gaussian noise. Here, we actually use a channel to give us privacy for free. I mean, this is actually what we have done in a recent work. Mathematically, you can write it very simply, very in a clean manner. So you can now write down your minimization of the test loss. And then what you do when you go from the digital to the analog case, you simply encode the channel, right? This is the channel multiplied by the model of the kind of worker I equals to the global model. And then you again run through your ADMM primal dual update. And you can show actually that this does converge without relying on any sort of heuristics, okay? Now, if you want to look at the result, in fact, here, so we were interested in communication efficiency, right? So this is a test accuracy, number of communication uploads. This is the digital approach, which requires a lot of resources to converge, right? Whereas the proposed analog one is really here. So it's very, very, very fast in terms of convergence. We are also trying to be nice to the digital one by giving it 10 times more resources. Still, you can see here, it takes some time before it starts to converge. So very competitive idea. Why not use it in some settings? Now, also from an energy efficiency perspective, you can see here, this is the digital approach. So these are my signal to noise ratio, right? So most of the time, the channel is noisy, right? So here you can see that we need actually to wait until 15 dBs before performance of the digital baseline start to really work, right? Whereas the analog one is really super high, 95 accuracy at a very, very low SNR, okay? Now, also in terms of scalability, let's say I want to guarantee 90% accuracy for, I'm comparing here, again, this is the digital and this is the analog. I really need a lot of resources, in fact, to really start to match the performance. So again, this is not going to be working in all the scenarios, but in scenarios, let's say in a factory, you can actually leverage this property of the wireless channel to give you really for free a model. Okay. Now let me move on to the second family. So this is the federated distillation technique, which is actually fairly easy, inspired by the work of Jeff Hinton. So here I have, in fact, again, workers, devices, right? And now instead of communicating the entire models, I'm sharing a logit. So I don't know if people know the logit. The logit is simply giving you a richer signal than a 0-1 kind of cat or dog. Here I'm getting this histogram giving me 20% dogness, 80% catness. Then you send this over the air to the server. Server then what it does, it distills this knowledge to the student. Mathematically, it's maybe easier to see here. This is your classical weight updates, learning rate, gradient of the loss function, plus this term here, which is in fact the structured regularizer calculating the difference between the prediction of the teacher, meaning all the other devices, and the student. If this difference is small, there's no need to do anything. So follow the same direction of the update. If it's not, then you add this regularizer. Okay, very simple idea. And now if you compare FL and FD, you can see now in terms of communication cost, huge gains. I mean, 10,000 times less communication overhead compared to FL, because of course we share the logit. But there's a bump in performance, as you can see with me here, in terms of 92% for test accuracy versus, let's say, 86%. Actually, this gap was bridged in a later work, so I don't have time really to go over it. Also, just to let you know, we can also prove, in fact, that using neural tangent kernel theory, you can actually show that the performance of the student does converge to the performance of the teacher. Okay. All right. Let's move on to the third family here, right? So we saw FL, we saw FD. Now there's another idea of split learning came up from the group of Ramesh Raskar, one of our collaborators here. As the name suggests, can I now partition this large neural network across many devices, right? And try to learn a model. That's essentially what we did. And I'll show you how we applied it in a wireless communication setting, right? So, I mean, there's a lot to say here perhaps, but I mean, in short, I mean, compared to federated learning, split learning can have actually any type of neural network architecture. This is number one, right? But also the way it works is different, because here what you do, you have this smashing layer, meaning you run your tensor, your forward tensor up to some layer, then you send it to the server continues the compute and then send you back the result, and then the labels probably are sitting at the client, because the client could be a hospital, right, or some other privacy sensitive setting. Okay. We can also use it in a wireless setting, because you may have, for example, a sensor which cannot run heavy computation, and therefore it will run, I mean, it will use this split learning idea to run few layers here, send the result to the server continues running those computations, and then maybe send them back or not, depending on the use case. All right. What was interesting for us now from a wireless perspective is we wanted to solve this very interesting setting, what we call blockage prediction in a wireless setting. This is a user, this is a base station, and you have a camera. And then what you want to do is you want to predict before the event happens. I want to predict before the user here blocks my link. Okay. Now, if you do it with a radio frequency signal, you cannot do it because you don't have enough data, right? So therefore, you cannot even predict that event. However, using multimodality sensing and fusion, we can actually learn a model that essentially fuses the information from both RF and camera to help us predict the event before it happens, right? That's a little bit what you see here. My receive power, the time. I want to predict the event before it happened, because obviously that's what's more interesting to us. And therefore, you could, consider many baselines. This is the RF one, the image one, and the proposed one is when you fuse really the embedding, you can call it, of or compressed representation of both modality, feed them to the base station, and then train a model to predict the future received power. Okay. Now, I think the results also are worth going over, because now what we do, of course, now what you have is a camera, right? You can see it here. This camera now has to kind of strike a trade-off between compression for the sake of bandwidth, right? But also in accuracy, right? So with that, you just play essentially with the CNN filter. You can see here going from raw images down to even 1 pixel, which is my 40 by 40 filter, where you lose information. But it turns out, in fact, that this 1 pixel information here, which is actually depicted here, is much better than relying on the RF signal only, right? So RF signal plus 1 bit information is better than just relying on RF. Now, of course, when you have both, you can see with me here, so by 4x4, which is this filter dimension, gives you the best in terms of accuracy and bandwidth. Okay, so that's essentially what we did, right? Now, all this track is very interesting, a lot of works, from our perspective, this is going to continue to evolve. But in fact, there is something else. And I'm happy to share with you this something else, at least through the lens of our communication world. So what do I mean by that? So now I'm going to talk to you about this VisionX, which in short is semantic communication. For that, as you maybe know, now we are talking about 6G research. Now, 5G is rolling out in the world, but 6G is really the new revolution. It turns out, in fact, that 6G promised a lot of things, connecting digital, physical, biological worlds. However, the current visions, in fact, are just an incremental evolution of 5G. Why? Meaning that the bigger, the better. A bit what I see in machine learning, meaning that add more bandwidth, add more base stations, and improve the performance. Or maybe if we have, let's say, some very tight requirements in terms of reliability, this is a packet error rate, let's now just multiply by 10, and let's call it a 6G. For some people, by the way, in my area, they just think that taking 5G and adding AI is equal to 6G, but as we know, this is not really true, right? Therefore, what we try to do is to flip really this paradigm, this bigger, the better kind of bandwagon, to ask two questions. First question is, can we actually transmit less and achieve more, right? And also, if 6G is really about human-machine collaboration and communication, then I think the solution is inside us, meaning the humans' two modes of cognition, System 1, System 2, which probably some of the audience is familiar with, made popular by Daniel Kahneman, and of course, Yoshua Bengio has been very, working on this area. So System 1 is your fast and conscious modes, right? So just static learning patterns from data, right? This is not the modes of cognition which we need, by the way, for communication theory, but also machine learning, because we're missing the planning and the reasoning part. This is exactly what's missing today in my area, meaning communication. That's exactly what's missing in LLM, I guess, right? So this is also where both areas are not colliding. So let me show you a little bit what I mean by that. So Shannon is the father of information theory. So as you know, in 1948, he wrote a very, very famous paper called Mathematical Theory, right, of communication, laying down 3 levels of communication, level A, B, C. So level A, very simply here, is take a message X, encode it, and then send it over the channel, make sure the receiver gets X equals X hat. It turns out Shannon, in fact, removed any meaning, context, structure, memory. Gave you X, give me X hat. In fact, what's a bit surprising, in fact, this is not really how the brain works. In fact, the Shannonian information is simply a statistical measure of information. Now, of course, he himself wrote a paper called the bandwagon, meaning warning us, do not use level A for biological systems, because in fact, there is this level B, level C. Level B is about extracting meaning from the sender, and level C is acting on the meaning at the receiver side. In other words, add meaning, add structure, add memory. Now, from my perspective, in fact, this is where the kind of inspiration came, because now, of course, what's the goal of communication? Well, in fact, for that, what's meaning? Well, that's, in fact, related to how do you learn concepts from data? How do you learn equivalence classes from your data, right? That's meaning in the abstract sense, not just saying this is a cat or a dog, right? And of course, information is no longer a scalar as in the Shannon world, so entropy of X, that's the ambiguity of my random variable, but information here lives in what we call a topological space, or for people more grounded in mathematics, this is the category of sheaves, or pre-sheaf in this case, right? So in short, what we need to pay attention to, I think even the ML community is really related to this, in fact, is that information is a shape or a space, and with that, we can now look at what semantics means. Is it from a category perspective? Is it from a logical perspective, right? And I think I wanted to also share with you this quote of René Thom, a very famous French mathematician, who actually hits the point by saying that when you use the word information, what you actually need to use is the word form or shape, okay? And again, what's semantic information? If you ask 10 people, you get 10 different definitions. So you can, maybe some people, they think it's the importance of a data sample. Some people think maybe it's the object in the image, it's a cat and a dog. Maybe just do Word2Vec or latent representation of my GPT-3. Maybe, I don't know. But for me, these are kind of low order information. What we actually need is a different notion of information as a set, at least to start with. So in fact, there is this very famous paper that came after Shannon by Carnap and Bar Hillel, which goes after the set values notion of information. So you see, we go from scalar to sets. You can also model it as a pre-sheaf of a Galois group, but you get the point here that we're going for more and more structures. So category theory is exactly the right tool here to investigate. Of course, if you talk to logicians, there's a lot of semantics, Kripke semantics, functional distributional semantics, and so on and so forth. And therefore, with this, we decided to kind of give it the system 1, system 2 connotation, so semantic communication, because we realized there is a big confusion in the area. So let me show you what I mean. So system 1, semantic communication, is everything we see around us, meaning this is about learning in data space. There's no notion of agencies. Humans are agents, right? So there's no supervised learning anymore here. You have to really be grounded in your environment, collect your data, and then train your model. So for example, there is this very simple idea here of one image, right? So take an image, and instead of sharing the image, what you do a transformation from image to text, send the text to a receiver, and then the receiver will kind of generate a different dot. By the way, this example came before even OpenAI was OpenAI. Okay, now this is not really what the human brain does. You can see it from a kind of semantic representation perspective. This is just about minimality and sufficiency of your model. Also, the task is simply still, again, reconstruction, meaning the receiver does not understand the concept of dot, right? And also, semantics is here really just the fresher, the better from a sender to a receiver, right? So it's also data filtering, perceptual compression, a lot of notions that machine learning folks are actually familiar with. What I'm after is the system 2 aspect here of semantic communication, which you can see through maybe the task. So here the task is really to reason and plan, as I told you, by compositionality. This is essentially what, of course, is very difficult to do, but that's essentially the kind of system mode that communication and cybernetics and ML are missing today. With that, you can go after use cases that 6G, in fact, promised. So, for example, what's the language that this robot in my factory are going to use? What's the signaling? What's the language, right, to solve a task? We also have it in the base station to user side. What is this language that actually the users are going to learn from data, right? And so on and so forth, right? But underneath it all, really, is mathematics, meaning we need a theory of abstraction, a theory of algebraic compositionality, and a theory of interoperability. These, of course, are common to my area, communication networking, but definitely machine learning. Okay, so what I'm gonna do now, I'm not tracking the time, is to walk you through some of our recent results in this area. So the first one is really called semantics native communication. Here, we wanted to answer this question, right? So how and under what conditions communication emerges between a speaker and a listener, or two agents, given that they may have different priors, different beliefs, right? So how would you do that? So you can see with me, this is a speaker, that's a listener. And what we did, in fact, is to leverage this triangle of meaning from linguistics, which says that, in fact, if you have a referent, an observable, never learn a mapping from the referent to the symbol in some sense, right? What you, of course, need to do is learn first the concept, right? Thought, and then verbalize that thought. That's in short what we did. So now we have a triangle here at the speaker, a triangle at the receiver, and then the receiver has to infer the intent, not the data, the intent of the receiver, which in other words will be about converging towards this common meaning space or topological space. And that's exactly what we study in this work. So in short, there's a lot here because in fact, what will happen is depending on the cognitive ability of the receiver, the sender may do different things. Maybe send all the concepts to the receiver or send minimum amount of concepts such that the receiver can decode. Right? So mathematically, of course, which is our interest, you can can formulate this in a clean manner. So this is done here. This is essentially the loss function of the speaker and listener. This is the joint entropy between the speaker's context and the mutual context. That's exactly where they want to converge to. That's the entropy of P divided by alpha, and likewise for the listener. You can see here, in fact, that this is just a kind of reformulation of rate distortion in concept space, or there's a famous Blahu and Arimoto algorithm that does that. What's interesting to note here, in fact, is this rate distortion or compression is about mapping different data to one concept or more concepts, right? So that's essentially what we did. So you can see with me here that we can actually show that this actually does converge. And I'm gonna skip this because I can see already somebody's after me here. So let me just go through this. This is just some result to show that the reliability of the communication will emerge over time, right? From 20 to 200 seconds here before you can get any sort of good performance. So I have five more minutes and then I'm done. All right. Now, another type of interesting works is to learn communication protocol entirely from data, right? So we call it, of course, system 2, but this is really early system 2. So what do I mean by that? So in fact, there is this idea of learning the 3GPP communication protocol between agents, a base station and a user, entirely from data. This has been done by, for example, Nokia Bell Labs. They just used a off-the-shelf framework. This is the RILE approach from Jacob Foster, for some of you who may know. And then they formulated as a cooperative problem and solve it. The problem with this, in fact, is back to the same idea of, is there any structure here? Is this any invariance, any symmetry we can leverage? The answer was no. And therefore, we tried to actually do that, meaning we did not learn the kind of mapping from state space to action space, but from information space to action space. Now, of course, this is this idea of what do you mean by abstraction? Is it in terms of features, symmetries, and so on and so forth? We took at first the compression in terms of cardinality, and we trained a model essentially to really compress this language in terms of obtaining its latent representation, and then generating, in fact, a lot of protocols or signaling, right? And then you can maybe see with me here that this idea of state abstraction outperforms any other baseline where there is no abstraction. This is essentially what we did here. I'm gonna maybe skip this just to move on to this last work we did, and I think may raise some interest, is we realize, in fact, my area, perhaps less machine learning, is we haven't exploited other type of mathematical foundations. So we looked at this very basic idea or fundamental question, perhaps, how can the geometry of the data be used as a state abstractor and data semantic for learning a protocol? So again, you can solve this in many ways, but for us, we really went after, let me just go here, we went after this idea of persistent diagrams, which comes from persistent homology, which allows us to essentially compress these observables in terms of a different space, which you can see here. This is gonna be my concept space. That's essentially what I'm gonna be learning my signaling, my protocol between the agents. So we use notions of, I don't know if you're familiar with it, maybe the homology, cohomology. I guess I don't have too much time to go up for this, but in short, what we were after is this barcode, which can encode the data semantics. So here I'm gonna get this barcode, in fact, that's gonna be used to learn this mapping again between how two agents can communicate. All right, and I think yeah, maybe for the sake of time, I'm gonna just skip this to perhaps go to my slide, just to conclude on this, right? So in fact, what we're trying to do here, and I'm sure that there are a lot of interest from ML perspective, is this one. We have a number of agents, right? Multimodal agents, so RF, radio, image, LiDAR cameras, and they need to communicate. Now, of course, this is actually a machine learning problem, but more importantly, maybe it's a more semantic communication problem. If I have data from a different syntax, and the other agent has a different kind of syntax, how are these two going to communicate, right? So this is very important. But for us, what we're really trying to do here is to really revisit everything, meaning we have been kind of bogged down in terms of information as a number, Shannon theory, but in fact, the right approach is to go after information as a shape, which means, in fact, we have kind of to step back a little bit, slow down the train of publications to really look at now different notions of information, right? Which I try to explain to you. Foundations of algebraic topology, category theory, and so on are actually a must-have nowadays, right? So, I mean, some of you maybe know that rate distortion is used everywhere, including information bottleneck, right, type of models, but that information is really not enough because you need to capture, again, more information than a scalar. You need to go after, this notion of shape and how to characterize this topological invariance of your data, right? And with this, thank you very much. Happy to take questions and maybe discuss. Thank you very much.
Thank you very much. Thank you so much, Professor Mehdi Bennis, for the insightful talk and very rich. We tend to.
Should I stop my slides or?
Yeah, that would be great. Yeah.
Okay, great.
We nowadays tend to go to the scale and scale everything to get a better results, but in other talks in this conference as well, there was an emphasis on focusing on more research, focused topics and areas. And so we'll take some questions. We have first questions maybe related to Moroccan context. So as Morocco, as you may know, still a transition to the 5G. So the idea or the way we transition to 6G, how do you see this transition going, or will be done, or what's the effect on the Moroccan landscape given the current infrastructure and the scattered maybe populations in some areas and centralized populations in other areas?
Yeah, sure. That's an important question. So 6G is good to look at it from two different hats. So the industry hat, the Nokia, the Ericsson, the Huawei. In fact, what we see today is that it's really just an evolution of 5G, meaning again deploying more base stations, going higher in frequency, right? Because that's where you have a wider chunk of spectrum, and you can leverage that to increase the connectivity, data rates, download your Netflix movie in 1 second. But in fact, that's not scalable, right? And therefore, from an academic perspective, we see in fact that the reason for that lack of progress is because we need to look at more fundamental theories in mathematics. For example, how do you communicate the meaning of the data, the semantics, instead of the raw data? So people call it compression, but in fact, there's something fundamentally novel there, which we don't have. We don't have the theory for that. And of course, for Morocco here, I mean, there are many messages here. The first one, my personal message is we should not put all our eggs in one basket, meaning just following what the industry is doing, because I hopefully try to show you that we need to slow down, work out more fundamentals, and with those, if those work, we will impact communication theory, information theory, AI, obviously, robotics. So I gave a talk after the Moroccan earthquake about this idea of deploying drones. So it's the same. You have different drones, different sensors. How can this drone now kind of locate deceased people under the rubble using wireless signal? This is not going to be an area for other kind of maybe modalities, but how do you share or glue this local information across this resource constrained aerial network? This is a kind of concrete use case where the theory is not even there, which again, because you need different notions of information, not Shannon information.
Exactly. So about the 6G and maybe beyond the 6G, 7G or 8G, how do you see or how do you envision this next generation of network? So yes. What would it be like in terms of changing how we communicate or how we...
So another thing I forgot to mention, but it's along the same line. Right now, actually, in fact, all the GPT things are happening in different modalities than wireless. So in fact, we don't have today a foundational model for wireless communication. But recently, there's been a kind of hype also to mimic what's going on in other areas to do telecom GPT. Perhaps this was presented by maybe Merwan Deba last year. But for there, again, the problem is we don't have data. We don't have compute power. So where are we going? You see, but this is essentially what's expected, projected to disrupt wireless communication. Just drop this generative AI in the base station, in the user, in the drone, and let them somehow figure out how to communicate better, faster, based on the resource constraints. Right. So this is exactly what's happening today. So call it semantic communication, distributed AI. For me, I see it as one kind of overlap between these areas, but we are going to hit the same wall that machine learning experts better than me, like Benji, say. We have to look for different foundations. 3-4 years from now, transformers is probably an old technique, right? Because we have to change a bit the mindset, because it's going to be otherwise the company that has more GPUs like NVIDIA, more data, right? There's some countries, but perhaps Morocco and maybe African nations should pick a different battle. Yeah,
exactly. Okay, so we have another question here. What kind of applications can benefit from curated learning in the Moroccan context? What kind of instructor is needed to be able to adopt these solutions in the context?
So there are many zillions of applications of FL that I have seen around. Some of them are related to hospital. You have different hospitals, private data of customers, citizens, so you don't want to share the private data over the air. I mean, there have been really a lot of applications. You can also do it perhaps at the level of, I don't know, let's say, sensor networks, because you don't want to share, again, if these are sensor networks on the human, right? So you don't want to share the kind of raw data of private EEGs or ECGs, so you want to share the model, right? I mean, there's literally 1 million applications one can think of. I have seen some like drones equipped with cameras, maybe trying to essentially track, count number of cattle, in an area. People have used federated learning. My issue with federated learning, as maybe people know, is it has a lot of issues because, this non-homogeneous aspect, the resource constraint aspect, it only learns a global model. We know that's not enough. You need to learn sometimes a personalized model, right, tailored to the user's preferences. But yes, why not? I mean, for us, we use it for, as you can see, this vehicular setting. It works very well. But if you have an asymmetric type of traffic between different vehicles, it will just not work, right? But yeah, FL, split learning also, very, very interesting areas. And of course, I have only talked about supervised learning, right? That's the kind of the elephant in the room. We must go unsupervised. It's much more difficult, but that's the way it is, right? So yeah, there are many techniques. Let's say GFlowNet, which is this nice framework developed by Selim Ben from Bengio's lab. Those kind of techniques are actually going to be extremely important to solve many of the issues I presented today.
We have to work on supervising the data.
Yes, absolutely, no doubt about it.
So maybe another question related more to the theme of the conference. How do you see the new role of telecom engineers and researchers, and is it changing? And if you have any advice for the PhD students or researchers working on the 6G or some research.
Yes, that's a very deep question. I mean, it needs deep answer, but I'll try to be brief. So going through. So in fact, when I started working on FL, I was one of the first ones in wireless communication. Obviously, we thought that we hit a plateau, that there's nothing new to learn. 2023, 24 now, I know that actually there's a lot of things we do not know. Okay, so I talked a little bit about, this idea of category theory, algebraic topology, concepts that in fact are either not taught at a graduate level or are taught in mathematical departments. In fact, what happened is kind of we divided all this mathematics in terms of silos. This is for computer science, this is for electrical engineers, and today we pay a heavy price. So for me, if I had to do anything, is to rebuild the educational system of Morocco or other countries by now trying to really train the next leaders, which have to be not only conversant in, let's say, statistics and probability theory, because that's the only tool we have used so far. That's why FL is a high school type of technique, sorry to say, right? But now, what does model averaging mean when I'm in a topological space? What's the idea of addition? What's the addition of equal, right? Equal, it's not 1 + 1 = 2 now. I have different shapes. How do I glue them? How do I find equivalence classes? Those concepts, no doubt, are key for communication, information theory, and definitely AI, right? So you see, I'm even internally in my group now, I'm trying to find a way to train the next people without having to spend 5 years to go and study that theory and this other theory. And hopefully I can manage to do that, but that's my advice in short, really, for Moroccan universities, because with that, you can not only catch up the hype, but have an even deeper impact.
Exactly, a more lasting impact. Yeah. Thank you so much for the insights. So maybe last word for the MoroccoAI community, maybe in French, if you like.
French. Let's see how my French works. Non, je ne sais pas. Bah, écoutez, d'abord, je vous remercie infiniment pour cette invitation. J'espère que le talk était intéressant. Il n'y a aucun doute que qu'il faut revenir aux fondamentaux. D'accord. Les Marocains sont très très forts, ont toujours été très très forts en mathématiques et physique. C'est pour ça que c'est les premiers en Polytechnique Paris et autre part. Donc il faut vraiment capitaliser ce talent qu'on a au lieu des fois de suivre un peu ce qui se passe. Ça, c'est mon expérience personnelle. J'ai aucun doute que peut-être les gens n'aiment pas ce que je dis là, mais mais vraiment, j'y crois personnellement. Et les Marocains, encore une fois, je pense qu'il y a une très, très, très grande opportunité à saisir, d'accord? Je pense que Benjio l'a dit encore mieux que moi. Un pays qui n'a pas de stratégie AI, mais j'irai encore plus loin, stratégie fundamental mathematics, aura des problèmes dans 10, 20, 30 ans. Et je pense que le Marocain peut jouer un très, très grand rôle. Voilà. Encore merci beaucoup pour cette invitation. C'était vraiment un plaisir.
Merci à vous. C'est un grand plaisir de vous avoir, Professeur Mehdi Bennis. Thank you so much for these last words. Thank you for the attendees, the MoroccoAI community. We'll see you in the next session. Thank you.
Thank you so much. Yallah. Assalamu alaikum.